Hello everyone, hopefully you're doing well. In this video, we're going to start with chapter 9. Chapter 9, we're going to take a look on modeling our world. In this video, we would focus most of all in some modeling, like climate modelings. There are different ones, but in the first sections in this chapter, so we call it Unit A, 9A, we're going to talk about functions, the building blocks of mathematical models. Remember, a real office complex may not look exactly like the scale model used to design it, but the model helps the architect to create the design. So a world map doesn't look at all like a real landscape, but it serves as a model of world system and can be extremely useful when you travel. So the purpose of a mathematical model is similar to that of an architectural model or a world map, right? It represents something's real and help us understand that real thing exists. So, more specifically, mathematical models are based on relationship between quantities that can change, you know. So, it's based on the quantities that can change, such as the relationship between wind wind speed and stress on a bridge, or the relationship between worker productivity and unemployment. These relationships are described by mathematical tools that we call functions. In a sense, functions are the building blocks of mathematical models. Some mathematical models consist of only a single functions, which can be represented with a simple formula or a graph. Other mathematical models, such as those used to study Earth's climate, may involve thousands of functions and quantities or variables. But the basic idea of a function is the same in all cases. That's very important. You know, so a function describes how a dependent variable changes with respect to one or more independent variables. Yeah, we could talk about dependent and independent variables because you know, that's very important to see. When there are only two variables, for examples, if we see f of x, or so we can say, or if we see x, y, x and y, we can say x is the independent variable, for example, independent variable. And you have y is the dependent variable. So that means y depends on x, right? As an example, let's say, for example, when we said, f of x equal y. So whether you call it f of x, a function, expressions in function of x, so we call it y. Let's say y equal 12x. Let's say 12 represent your hourly wage. You know how much money you get paid per hour. X represent the number of hours you work. So you see, Y depend on the change of X. So if you never work, then you would have no money at all. But if you work 10 hours, 10 times 12 give you $120. So meaning if you work 20 hours, so it's gonna have $240. So you can see that Y depend on X. If X never change, Y would never change. So we have already used functions several times, in this book, especially in chapter 4, we did it without calling them by name, because in chapter 4, we saw exactly how the balance in the saving plan is related to the interest rate and the monthly deposits. So in chapter 8, we saw how population is related to growth rate or time. So these relationships are functions because they tell us specifically how one quantity varies with respect to another quantity. So, you know, um, like talking about dependent and independent variables as you see here, because we said when there are only two variables, they are often summarized as an ordered pair with the independent variable, like first variable first, independent variables, and dependent variables. So that's why I said we call them X and Y. So the dependent variable is a function of the independent variable. If X is the independent variable, so as I said, Y is the dependent variable that we can write it is like Y equal Y f of X, as we said, it's a function of X. So the quantity related by functions, we call them variables because they change or they vary. So examples, temperature is you know, can be dependent variable because it depends on time. So time is the independent variables, right? Because if we talk about temperatures data for one day, so because you know, if the day never change, probably the it would never change. Okay, so the temperature would never change. So that's what happened. Now we're ready to take a closer look in some functions because remember, in terms of functions, you would always have two variables. One would be x, the other one would be y. If you don't want to call them x and y, let's say one can be time, okay, as the independent variables, and temperature would be, the second one. You can also have some where you we talked about hours worked, and salary, right? So salary. So one would be, it's all depends. The salary depends the number of hours you work because the hourly wage is fixed. So as long as we can find, we can write related variables in the form of an ordered pair with the independent variables first and the dependent variables second, we are all right. We use special notation to represent functions. Like we always like we use X to represent the independent variables and Y to represent the dependent variables. So the dependent variables, that's exactly what we do here. So note that when we say that one variable depends on another variables, we do not necessarily mean that one variable causes the other variables, right? We don't say, oh, you know what? The number of hours you work causes that you have a salary. That's not true. You may work for free. So it's all depends. We need to pay attention to this, that. So a function is simply a relationship among two or more variables, and it may or may not be a causal relationship, right? So very important to look at it this way. We're gonna go over a few examples. In this one, they ask you to, they said, in each of the following situations, state whether two variables um, are related in a way that might be described by functions. If so, identify the independent variables and the dependent variables, right? So for the first one, they said you jumped from an airplane, right? For A, we said you jump from an airplane with parachute and want to know how far you have traveled at a various times during your descent. So how far you want to travel. So in this case, you're looking for your distance with respect to time, right? because in this one you are really interested distance with respect to time. So this is a functional relationship, It's a functional, it's a function, right? It's a functional relationship, right? As I said, with time as the independent. The time is an independent variable, right? Independent variable and right? Independent variable and distance fallen is the dependent variables, right? Is the dependent variable. So that's how we're gonna say it. Remember, we said you jumped from an airplane and want to know how far you have traveled at various times during your descent. So we said you want to know the distance you travel with respect to time. So, like do you do 25 miles per hour? Do you want to 25 miles for 20 minutes? So it's all depends. But if you never go over the time, you would never find it. That's why we said time is the independent variables. So we can even try another one. Let's try B. Okay, or we can try well, I'm gonna try B. Okay, maybe I might not write all of this just to save us times. For B, it says each day for several weeks, you record the number of calories you consume during the day and the number of hours you slept that night, right? So let's see. Each day for several weeks, you record the number of calories. So it's calories per day, it's calories over a certain period of time. So that's functional, right? Calories over a certain period of time. So that means time should be the independent variable, right? So it's a functional relationship with calories consumed. No, calories consumed is because if you don't consume calories, you may not know whether or not it's affect your sleep, right? So calories is the uh, independent variable. Hours of sleep is the independent variable. So is the dependent variable. So independent. So you can rewrite it as I write A, but I just write. So calorie consumes each day. Calories consume each day. Now, dependent variables. Dependent variables would be hours of sleep and of sleep. And we can say this is really a functional relationship. So this is a function. Not all the time it's gonna be a functions. If you look at D as in dog, probably, maybe you can see that we said you walk through a used car lot and list the price and model year of each car you see. Well, the problem, this one cannot be a functions because look at model. They said you list price and model each car you use. So in this particular case, there is no obvious functional relationship between the variables because two cars of different model years could have the same price. You can have two different used car, but has the same price or two cars of the same model year could have different price. So this one is not a functional relationship. There is no functional relationship with this one where you can say, oh, this is a independent variable or is a dependent variable. So that's at some point something you need to pay attention to before we get any further. So talking about functions, I think so far you understand that function is simply a relationship among two or more variables, and it may or may not be a causal relationship. But representing functions, there are three basic ways to represent a functions. We can represent a functions with a data table, okay? Like a table can provide detailed information, but it can become unwieldy when we have large quantities of data. Use the with table, data table. We can draw a picture or use a graph to represent the functions. A graph is easy to interpret and consolidates a great deal of information. And the third way we can use to represent the functions is we can write a compact mathematical representation of a function in the form of an equation or formula, like Pythagorean theorem. So or if you know the formula how to find the perimeter of a rectangle, how to find the circumference of a circle, how to find the area of a trapezoid, right? So we have so many different ways to find volume, etc. So sometimes we use formulas, sometimes we use graph, or we use tables. So pictures is one of them as well. So how do we go with that? We understand that a functions usually if we can graph using an XY coordinate planes. So this is the coordinate plane. This is an XY plane. I can call it XY plane. The reason why I call it XY plane, we can represent a point that has two coordinates. That means we have X coordinate and we have Y coordinate. So one point has two coordinates, one X coordinate and one Y coordinate. For example, the XY plane is a vertical line and a horizontal line intersect at the origin. So that means here you're gonna have 0. So on the horizontal axis from 0, if you go right, you're gonna have positive numbers like 1, 2, 3, 4, and 5, and 6. I put the arrows, that means it goes indefinitely. Below 0, we're going to have the negative numbers like -1, -2, -3, -4, etc. So above 0 on the vertical line, that would represent Y. Remember, the horizontal line represents X coordinates. Vertical line represents Y coordinates. If you go up above 0, you have the positive values for Y that you can list indefinitely, right? But for me, here I put them like I go up to 4. But remember, that's not the limit. You can go as far as you want. Now, if we go below 0, that will be all the negative numbers for Y. Okay? Now, if they ask you to plot certain points, like, let's say plot X equal to 3. So when this one is X and this one is Y. So if I want to plot this point, I count on the X axis, the horizontal axis 2, and I go 3 units up because that's where we're gonna have 3. So that's where we're gonna have the point 2, 3. Remember, if they give you one point that is negative, for example, if you have point like -2, 1, that means X is -1. Remember, we go on the left of 0 and going 1 units up to say, oh, you know what? This is -2, 1. And if they give us points like -4, -3, that means X is -4, going down 3 units on the y-axis. So intersect here, that would be -4, -3. Or we might be on the side where if we can have other numbers, like let's suppose we have 3, -2. So x is positive 3 and y is -2. So we go in on this corner right there. So we write 3, -2. Other characteristic of a XY plane, or we call it coordinate planes. Remember, we have 4 quadrants going counterclockwise. So we call this part, because anytime we uh, uh, divide, uh, you know, two lines, one horizontal, one vertical, intersect to create an XY coordinate planes. We call it divide into 4 quadrants. We call this one here quadrant 1. Counterclockwise, this is quadrant 2, quadrant 3, and quadrant 4. Now, it all depends on what you're doing. You might fall in any quadrant or you might fall on the axis. For example, if we go here and they ask you to do negative 2, negative 30, that means x is -3, y is 0, so we're gonna be right there on the axis, right? So it all depends of what you do. So you're gonna be on the x-axis negative. So it all depends where you're gonna be, but it's very important to review the coordinate plane, because this is the most common way to draw the graph of a function. Really, is to use that coordinate plane, which is made by drawing 2 perpendicular number lines. Each number line is called an axis, right? We have x-axis or y-axis. Normally, numbers increase to the right on the horizontal axis, like 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. Or it's also increase upwards, like on the y-axis, so again, and or on the vertical axis. So the intersection point of the two axes, where both number lines show the show the number 0, we call it origin. So if we are working with a general function, the horizontal axis is called x-axis, the vertical axis is called y-axis. All right. So points in the coordinate planes, we describe them as an ordered pair consisting of 2 coordinates, x and y. Hoping that's helped a lot, because it's important to give you an idea of these points. So now that you see this, it's very important also to introduce what we call the domain. In terms of domain and range, we said before we draw the graph of any functions, we must determine the variable that we should show on each axis, right? So mathematically speaking, each axis on a graph extend to infinity in both directions. So when I draw that XY plane, either on the horizontal axis or vertical axis, I can continue indefinitely. So there is no limit on what value of x or what value of y, either positive or negative, I can possibly use. I can go indefinitely in both sides, either going to negative infinity or positive infinity. So there is no problem to do that. But most functions are meaningful only over a small region of coordinate planes, right? So that's very important to see that. So that's why for us, it makes more sense when we put a limit to it. In fact, the only times of interest for a functions, is when we can say, oh, you know what, we have a limit. So what we're gonna call everything that has to do with x-axis as a domain. The domain, it's all about the values that x can take. So domain is about x, okay, about x values. The domain of a function is the set of values of the independent variables. I don't want to call only independent variables. Independent variables, of course, because we might draw that XY plane and we don't call it XY. Maybe it would be T and something. So, but here we would consider x as our independent variables. So the domain of a independent variable, the domain of a function is the set of values for the independent variable that both make sense and are of interest of a function. For example, a functions like if I said f of x equal 2x plus 5, okay? But remember, f of x is also y. I can either if you don't like writing it this way, you can say y equal 2x plus 5. Now, looking at a functions like this, you said, what is the smallest number you can plug for x here? I mean, what number x cannot take here? Well, you may not have a calculator to do it, but there is no limit. You can plug x to be anything you want. So in this case, the domain would be anything, or you can say the domain would be all real numbers because there is no limit to what you can plug in that functions. And it's the same thing for the range. The range of a function consists of the values that the dependent variable. So meaning for the range, it's about y values. So the range connect to y and the domain connect to x, right? Very important. And it's to understand what is the smallest number or the largest number. I'm going to give you another examples. If you have y equal x minus 2, right? So what is the smallest number x can take here? Well, you cannot say x equals 0 because if x is 0, you're going to have 0 minus 2 is negative 2. And you cannot extract, square root of negative 2. Square root of negative 2 is not a real number. So remember, you cannot take the square root of a negative number. So for any x that would make these functions negative, so you said no, it cannot be there. You cannot take any negative numbers. You cannot take 0. You cannot take 1. You cannot take 1.9999999. So the smallest number you can take here is 2 because 2 minus 2 is 0. Square root of 0 exists. That's 0. But square root of negative 1, not a real number, right? So with some examples, we'll have chance to do more and more in this section. But you know what? We also need to talk about how to create a model, right? You create a model or how to create and using graph of functions. So far, we have plot points. So I'm hoping you know how to do that. But a model predictions can be only as good as possible if the data and the assumption from which the model is built. So first of all, when you create or using graphs of a functions, you must identify the independent and dependent variables of the functions. You need to identify the domain, that means the values of the independent variables, and the range, that means the values of the dependent variables of the functions. You use this information to choose the scale and labels on the axis. So you want to know the horizontal axis, would you call it x? And the vertical axis, what you call it y. Remember x independent and y dependent, right? So that's what you need to remember. Zoom in on the region of interest to make the graph easier to read. Make a graph using the given data to plot points. You need a few points. It's all depend of the type of functions you're doing. If appropriate, draw a line or curve to connect the data points. Now, before accepting any predictions of the model, be sure to evaluate the data and the assumptions from which the model was built. Very important. We have so many things we can do using a models. And if you have any chance to check in the book, I would advise you to go in that section because we're gonna use one of these particular tables uh, in this graph to answer a few questions. But first, We're gonna just go and follow an example solutions they give us to answer a few questions. So the first questions we're gonna answer here, write a short statement that express a possible relationship between the variables. So they give you only age, shoe size. Now they give you only two information. That means age, shoe size. That means would you agree that age is independent variable, shoe size is the dependent variable because the shoe size change only over the age. So if age never change, so shoe size would never change. So as a child, age, shoe size increase. Once the child is full grown, shoe size remain constant. So you make a big sentence. Now they give you two variables, two coordinates. Like for us, the first one is independent and the second one is dependent. Very important, we're gonna see it this way. So they give us a volume of gas tank and cost to fill a gas tank. So how would you construct your sentence to represent this? Well, following this one, we can say as, because they give us an example, right? We're gonna write it the same way, as the volume of tank increase, as the volume of tank increases, all right, the cost of filling it also increases. The cost of filling it increase. All right. So we can write something like that, right? This is just a very simple examples. I'm gonna leave B, C for you, or if you let to B. So what would you say for B? Because they give us latitude, ocean temperature on a given day. So we know latitude would be the first one is the independent variable, the second one is the dependent variable. But if we want to write something like that, the temperature we can say the temperature, right? The temperature of the ocean on a given day of the ocean. I'm not gonna write everything of the ocean on a given day. Uh, is that increase or decrease? Decrease, right? Of the given day decreases as latitude. Increase or decrease? Yes, increases. Yeah. Some very simple examples, but I'm trying to do the one that's short. Rate of pedaling and speed of a bicycle. So if you have rate of pedaling and speed of a bicycle, we said in a particular gear, the faster you pedal a bike, the faster the bicycle will go. So we remember that the answers may vary, but I give you some different ways you can do it. So I said in a particular gear, okay, the faster you pedal a bike, the faster you pedal a bike, the faster the bike will go. Okay. the faster you pedal a bike, the faster the bike will go. So um, that's very important. Okay. So it's very important to see it that way. We can see so many different examples as we go forward because I try to put as many examples for you to practice. For this one, again, there are a few tables that you can eventually use. One of these, as I said, those are tables we covered at some point through the textbooks. For this one, it's about completing the model also. We said for these examples, we can try to explain certain things. Use that table you see, 9A, 9A.6 and the figure, and the table 9A dot 2 to answer the following question. So I try to copy paste, but because those are things you can find also in the textbooks, but I put them here. So use that figure 9A.6, okay, to estimate the pressure at altitude of 8,000 feet, 6,000 feet. So first of all, you need to see where 6,000 lies. The pressure of 6,000, 6,000, where would you say 6,000 would lie? Somewhere here, right? No, no, that would be more than that, less than that, right? Because if you said 6,000 feet, probably is 5 is here. Yeah, 6,000 probably here, right? So if you go all the way up there, is that pretty close, right? I think at some point we can say that 6,000, the pressure of 6,000 feet is about 24 inches of mercury, right? So for BA, pressure of 6,000 feet, right, is about what? Um, is about, it's a projection. You can do that. It's about 24. Remember the horizontal, uh, the vertical axis is about the inches of mercury, about atmosphere pressure. It's about 24 inches of mercury, of mercury, right? But how about the 18,000? 18,000 is about what? Can you look at 18,000? Because 18,000 is pretty close. You see, this is 15. So going 18, we're pretty close to 20. So if we go 18, probably this would be 18 right there. I could put 18K. So if you go, where do you think 18K would lies? Like 15, or I would say 16. We're gonna say 18 feet is 18,000 feet is about 17 inches of mercury. With a ruler, you can see it pretty close because I use a ruler when I did it first time. So check that. And I let the 29,000 for you. I think you can find the 29,000 because 29,000 would be probably here going up like this. So we can say that 29,000, maybe about 11, right? Would be 11 feet. Now, B, they said use the same graph to estimate the altitude at which the pressure is 23, right? Now it's going the other way around. Um, now you want to know 23, where 23 would be. Let's see what I just did. If I put 23, 23 is somewhere here, right? is between 25 and let's put 23 here. And you go that way and you go down with a ruler, putting that here for 23. What do you think 23 would be? B? Mm-hmm. The altitude is about 8,000. For 23, I'm gonna say for 22 inches of mercury, the altitude, what is the altitude? Is about 8,000 feet. Well, that's what I can see. I can see the 1,000 feet. Now, if you want to do 19, 19 is under 20. Just erase all of this and let's try 19. So I think 19 would be something right there, right? If we go 19 like this, do you agree that 19 would go down like, right? So that would be about 14,000, right? Because we're pretty close to Kent. So for 19 inches of mercury, the altitude is about 14,000 feet. Okay. Now we said send the graph in 9.6 at about what altitude would the atmosphere pressure reach 5 inches. Oh my God, this is 5 inches. Let's go very quickly. Let's go. I'm gonna use a different color just for you to see. Let's go with red. If we go with a line, so then you choose to go with this. Where you think that's gonna go? Well, for 5 inches, I think it would be reach about 50. 5 inches, it would reach 50,000, right? That's what you can see from this one. But we have so many graphs we can read. I strongly advise you to take a break and look through these examples because we have so many of them like that. We can try to answer some questions very quick. Next, I think for this one, they ask you to use this figure again. It's in the textbook, which applies to 40 degrees north latitude. Use the graph to estimate the number of hours of daylight on daylight on April 1st, the 91st day of the year. October 31st, the 304 day of the year. So this is, we need to use to estimate them. So that's very kind of easy to see as we go over the daylights, right? So for us, you know, 91 days. Okay, can you check the 91 days? Because 91 would be probably somewhere here, right? Where do you think 91 would bring us? No, nope. No, that's not 91. Sorry, I think I messed up with 91 because 172. I'm gonna try to take a different color again. Let's put it. So 91 is pretty close to 80, right? So let's say 91 is somewhere here. I'm gonna move this because I try to do so. 91 is here, so it's about 91 days. This one right there, we can say on April 1st there is about 24 hours. About is that 24? No, no, no. There is about 12.4. 12 or 12.4 because it all depends about 12.4 daylight. October 31st is somewhere 304. This is 365 right there. Oh, we have 264 here. Maybe 365 should be somewhere here. 304. So where do you think 304 uh would bring us? 304, this one right there. About how many days light you can see it's 10 point something, 10.7 hours daylight. So it's 10.7 daylight for this one. Okay. And of course, yeah, as I said, you can look at these examples to do more. I do one for you from this graph. Please feel free to read and understand. It's just the interpretation of graphs, you know. That's not something very complicated. We can just answer a few questions. In these the next examples, what they ask you to do here, consider the following graphs of functions. You know, all they ask you to do in these particular ones, you need to identify the independent and dependent variables and describe the domain and range. So here, the independent variables here, okay, we can see it. Independent, sorry, it's here. Dependent is world populations, right? Because for this one, the independent variables is time. You know, if you want to call it times in years, I'm gonna change it. Time in years. And dependent variables, you see world populations, right? The dependent variable is world populations in billions. All right. Now, what they ask you to do for this one, identify the dependent and independent variable and describe the domain and range, right? So for us, the domain is the set of years, right? Look at the domain where it's at. Domain set. Remember, domain is all about the independent variables. Here, set is a set of years from 1950 to 2000, right? The range, what is the range? You can verify and tell me the range. The range is the set of population values, set of population values in billions, right? We would say in billions, we're gonna set, we're not gonna put all of them, right? Because we identify the domain and the range. The billions would be between what? Look where you are, right there, above two, right? Range between what? It's range between 2.5, I would say. to 6 billion, right? So that's mostly what we said. They said describe the functions in words. If you want to describe a functions like this in words, a function shows a steadily increasing world population, right? Function it's a B show function shows function shows a steadily increased population because there is no increased population. All right, so for the first time, they ask you to look at this graph. You need to identify the independent and dependent variables and describe the domain and the range. And after you do that, the horizontal axis always show the independent variables. The vertical axis show the dependent variables. Looking at this graph, you see the population keep increasing, over the years. Now, if you look at the second graph, probably it would be a little bit different when you look at the second graph. The second graph only show you, you know, the variables is times in years again, age. You see the independent variables for that one is age measures in years, and the dependent variables is weight. Remember, this is dependent, this is independent, this is dependent, right? And then the domain here. The domain is everything on age from 0 to 40 years. That's what we have here. That's the domain. The domain is the set of age between 0 to 40 years, and the range is all weight between about 7, 8 pounds to 130 pounds. So we can go with that and you describe it. I believe the last question is about the same type of questions, but in this case, we need to see it differently for each of the following data tables represent, identify the independent variables. Here again, you know, independent variables here would be the altitude, right? So we're gonna take the altitude as the independent variables, right? The independent variables here, altitude. I'm gonna say this one is independent and this one is dependent, right? Dependent, independent. Identify, independent, and describe the domain and range. You see the domain, it's all altitude from 0 to 9,000, right? That's the domain. Altitude, the set of altitudes from between 0 and 9,000, and the range, the temperature between about 193 something to what is the largest number? 212? Yes. Well, the smallest one is 193, or there is a 90. No, we're gonna say about 90. Okay? Between 90 and 2000 and 212. So you can make a clear graph of this. Of course, if they ask you to construct the graph, you can do it. That's something I let you to do because you know the independent variables are the x-axis and the y-axis is the dependent variables. Then you can construct a graph for each corresponding point. Each point, let's say 0 correspond to 212, 1000 correspond to 210, etc. So on the xy plane, because you don't have any negative numbers, you can use something like that where you start with 0 here and you finish with 9,000 somewhere here, and putting all the numbers like 1,000, 2,000, etc. until you get to 9,000. Here you can start with 190 to 212. Now each corresponding point you plot it here. Think that's it. That's what we're gonna stop here for these sections and come back to talk about linear models in a different video. Let me know if you have any questions. I'll see you in the next video. Take care.